Hello, good morning everyone. Thank you so much for the introduction and thank you so much everyone for joining this presentation. We are going to introduce Omyasphere, which is a lightweighting and insulating solutions portfolio. This is the agenda that we are going to follow during the next 15 minutes. We'll be introducing the lightweight fillers technology, one case study for high reflective coatings, and we'll be presenting the smart combination that we have developed together between Omya and Kronos, combining Omya hollow glass microfields and titanium dioxide from Kronos. First of all, I would like to explain what are the main benefits of using hollow microspheres or lightweight fillers in paints and coatings. Of course, by reducing the weight of the final product, when we are introducing this material and replacing a significant volume of fillers in your formulations, we'll be able to make the final density of the coating lighter, and we will be able to bring savings in terms of transportation, and also will make we'll be making safer the handling of the paint. Another benefit by using hollow microspheres in your final formulation and replacing part of the filler is to increase the yield, to increase the coverage, right? Because we'll be able to do more with less. It will be needed less material for covering the same amount of square meters. And last but not least, and we'll be presenting in 2 days because it's part of the solution that we have developed with Kronos, that we are going to improve the insulating property, right, with this technology. There are different technologies of lightweight materials. There are, in fact, 5 technologies very well known, and they have been used in paints and coatings since many years. From Omya side, we have been focused on the development of the expanded perlite and also of the hollow glass microfields, that this is today's presentation will be more focused on this. And of course, each technology is more or less suitable depending on the application. As you can see here, depending on the target market, if we are more focused on paints, coatings, deco paints, insulating paints, we can select the more suitable technology. As mentioned before, for today's presentation, we'll be focused on Omyasphere 900 series, which is a hollow glass microsphere. I would like to present a real case study that is for high reflective coatings, but I would like to explain why we have selected this case study, right? Because I guess that for all of us, it's really well known the issue, the challenge that we have in the industry, right? I would like to mention that based on different studies that has been carried out during the last years, the conclusion is that 1/3 of the total energy consumption that we have today is mainly from the building sector, and the residential building sector accounts for more than half of the electricity consumption. And last but not least, in some well-developed countries, the air conditioning accounts for 60% of the total residential energy use. And as you can imagine, this topic for the high temperatures is not going to stop. We can see that every year the temperatures are increasing. Therefore, this is an issue, or this is a challenge that we are going to see during the upcoming years, right? During the last years, it has been developed different solutions. One of the solutions is the high reflective coatings, that we are talking about coatings with high amount of titanium dioxide, with customized fillers, with a specific particle size, a specific brightness, and especially the mechanism for these high reflective coatings, right, is based on 15–20% of titanium dioxide to improve the reflectance of the final coating. However, during the last years, with the new lightweight fillers and microfields that has been developed, we can see that we can capture more benefits, not only from the solar reflectance, also because by using this material, as we will see now, we are going to improve the thermal insulating properties overall, by reducing the thermal conductivity, by reducing the diffusivity and the emissivity. The combination that we have developed for these high reflective coatings is containing the titanium dioxide from Kronos, 2160, and Omyasphere 900 series, our lightweight material. And the main purpose that we have developed together this solution is for achieving the best cooling effect in paints, right? And also with a super high brightness, right? Because we are trying to combine the combination of both the titanium dioxide and hollow glass microfields for maximizing and for boosting the insulating properties of the final paint. The titanium dioxide that has been used in this case study is from Kronos, is 2160. The main reason why we are selecting this product, right, is because we already know that in terms of durability is one of the most effective one, and also is one of the brightest titanium dioxides, right? The hollow glass microspheres that we have been using is Omyasphere 900. This is a hollow material. It has a spherical morphology. It's a perfect sphere. It has a very hermetic surface. It means that the absorption will be rather low, and also it has a high mechanical strength, which is allowing to use this product in spray apply applications or even in mid-high shear conditions. Last but not least, this hollow microsphere is one of the widest material available in the market. You can see here the complete portfolio that we have for hollow glass microspheres. In the case study that we are going to present in the next slides, we were using this product with particle size D50 45 microns, D90 70 microns, and density 0.22. Keep in mind that when we are going to introduce this light material with density 0.22, and we are going to replace on the volume basis the calcium carbonate or other fillers that we can have in the formulation, we have to keep into consideration this density difference. In the next slide, you can see already the formulation, right? On the left side, you can see the roof coating formulation, the standard one, and then the formulation containing 2.8% of Omyasphere 922S. And in the right side, you can see already the volumetric approach, right? When you see 1 liter of paint for both formulations, you can see that both paints has the same amount of water, the same amount of additives, the same amount of titanium dioxide, the same amount of binder, and even the same amount of filler. The main difference is that in the standard formulation, 16% of volume is with calcium carbonate. However, in the formulation containing hollow glass microspheres, we are replacing huge amount of volume of calcium carbonate by replacing with hollow glass microspheres. Then both paints were produced, and you can see in the next slides the results. First of all, the formulation non-containing hollow glass microspheres achieved density 1.4, as it was already expected in the theoretical calculation. The formulation containing hollow glass microspheres going down to 1.03. Also, after 10 days aging at 60 degrees Celsius, the stability was really good for both paints. The optical properties didn't change in 300 microns gap. You can see that the main properties, RY over white, RY over black, contrast ratio and lightness of the final paint, they were remaining at the same level, something that it was already expected because we were keeping the same volume of titanium dioxide in both formulations, right? And at the end of the day, we were keeping the same volume of each raw material in the formulation. However, one of the key benefits of using this technology based on hollow glass microspheres and replacing significant volume of filler is the elongation, right? We can see that there is a huge improvement in the elongation. In the reference formulation, we were achieving 111%. When replacing part of the filler and introducing hollow glass microspheres, it was achieved more than 360%. There is a huge improvement, a huge increasing on the elongation. Last but not least, we were testing all the thermal insulating properties, right? First of all, we were testing the solar reflectance, that is very well known, that is the fraction of solar energy that is reflected. Also, we were testing the emissivity, which is related with the ability of the roof surface to radiate heat. But also, we were testing two parameters that are getting very popular, right, in the industry, which is the thermal conductivity and the thermal diffusivity, right? And I would like to explain that, well, even is well known for all of us what is the concept of thermal conductivity. For this kind of coatings, it's a very relevant parameter, right? Because it's going to give a clear indication about the capacity of the coating for transferring heat. And last but not least, the thermal diffusivity will give a clear indication about how fast and how well the heat will be transferred. In the next couple of slides, you will see the results. First of all, according to the STM E903 for measuring the solar reflectivity index of the final coating, as it was already expected, it was an improvement, 2 points of the solar reflectance, right? Then it was a clear benefit replacing part of the filler in our formulation by introducing hollow glass microspheres and, of course, using the right titanium dioxide from Kronos for achieving this 2% increasing in the solar effectivity index. And something that is very relevant is the improvement on the thermal conductivity, right? You can see that when using hollow glass microspheres and replacing part of the filler, we have heavily reduced the thermal conductivity that, as I have mentioned before, it will be fully related or fully correlated with the capacity of the material for transferring heat. The lower the thermal conductivity, the better insulating properties, right? And we can see that just replacing part of the filler and introducing hollow glass microspheres, we have been able to reduce more than half the thermal conductivity for 0.58 going down to 0.23. And the same for the thermal diffusivity, which is related with the capacity of the material for the speed, for how well, how fast the heat is going to be transferred, right? And also with the cooling touch that we can have in the surface. And there is a huge reduction of using when using this material. Last but not least, we were measuring with an infrared camera how looks like the temperature profile, right? After a few minutes with an infrared lamp, we were monitoring the heat build up, and you can see that there is a 3-4 degrees temperatures difference between two different coatings, one reference without hollow glass microspheres and one with hollow glass microspheres. And this 3-4 degrees that looks like is a small difference is very relevant, right? Because there are some studies that are saying that 1 degree temperature reduction means 5% energy savings, right? Then by reducing 3-4 degrees Celsius, we can easily achieve 15-20% savings in terms of cooling, right? In terms of energy. After this case study, we would like to finish this presentation mentioning that, well, thanks to this highly engineering combination of titanium dioxide from Kronos and light with fillers from Omya, we have been able to develop a solution for improving the insulating properties of the final coating when using hollow glass microspheres like Omyaspheres. We'll be able to reduce the density of the final coating. We'll be bringing clear and tangible savings in terms of transportation, right? We'll be improving some mechanical properties like elongation, as we have mentioned before. And last but not least, the main goal of using this technology is to bring cooling energy saving, right, in two different mechanisms. From one side, increasing the solar effectivity index, but on the other hand, by heavily reducing the thermal conductivity and thermal diffusivity of the final coating. If you want to experience this, also you can measure yourself both quantities, right? You can pass by in our booth. We are in Hall 3C, booth 114, and you can see already these infrared lamps that you can feel already the experience, and you can see already all the benefits that we have mentioned today in today's presentation. Thank you so much.